Hello, this short presentation is about single flux quantum logic and how it works. And this is a primer or introduction designed for circuit designers, not so much for PhD physicists, meaning that it will lack some of the details that a serious physicist might want. This is more about the simple explanations of what's going on and understanding so that you can design circuits. Okay. To start off, we'll talk about superconductors. What's going on inside of a superconductor? And here we have a picture of a normal metal and two different superconductors. And in a normal metal, the conduction, their free electrons typically have high density and scatter frequently. So, and whereas in a superconductor, you have these Cooper pairs. It's not exactly, they don't exactly pair up. It's a collective phenomenon, but you can think of them as pairs of electrons. And they condense into a ground state with an energy gap that's on the milli-electron volt level. So they're small voltage, small energies. And as bosons, there's no limit to the number of Cooper pairs that can be in the same state. So they condense down and they can fill up this state. Okay, so when we apply a current to a normal metal, the free electrons frequently scatter, so they have a low average drift velocity. Whereas in the superconductors, you have Cooper pairs, they don't scatter, and um, they're going to have the lower the density, the higher the velocity of the pairs to carry the same current. And the velocities can become very great, such that the kinetic energy of the pairs is significant, and inductance has to include the kinetic energy, the kinetic inductance. Um, okay, and if we have a loop, we have they will have the Cooper pairs in the loop. So you've got those. And then if you apply a magnetic flux externally, and we've got a flux applied showing if you do the right-hand rule, the vector of the direction of the magnetic flux is up. So, and this will induce a current in the Cooper pairs on the outside of the superconducting loop in the opposite direction to cancel, so there's no magnetic flux in the center of the loop. Now, um, because it's a superconductor, the magnetic flux within the loop is quantized in units of the flux quantum. It's a small number. And because the wave function must be single valued, the wave function of the superconductor in the superconductor. Now, if a flux quantum goes inside, they're going to be one flux quantum at a time. Okay. Now let's look at a Josephson junction. Um, we have a superconductor, that's the blue area, and it has Cooper pairs that form by condensation. And in between the superconductor, you have this gray zone. This is a barrier. And this could be an insulator. It could be a normal metal. Could be a ferromagnet, a ferrimagnet. It's a non-superconductor, some barrier. And there can be tunneling or leakage of the Cooper pairs into the barrier. And this is kind of showing from this side, looking up the density of the Cooper pairs as like an exponential drop in the barrier, and from both sides. So there's a little region where they overlap, and some Cooper pairs can tunnel across. Okay, so if we apply a current, there's a relatively larger density of Cooper pairs in the electrodes and the superconducting regions above and below, and so there's a low average velocity. But in the barrier where there's a smaller density of Cooper pairs, the velocity has to be larger to carry the same amount of current. And at sufficiently high velocity, the Cooper pairs, the energy becomes too great. They become greater than the condensation energy, and the Cooper pairs break apart. And you get a voltage across the junction. That's in a circuit. Um, okay. And this, an analogy to this is a little bit like a venturi, where you have flow, you have atoms, gas atoms flowing or molecules flowing in the venturi, the ends, and then when they get to the constriction, they actually have to go faster. Not a perfect analogy, but you could think of it a little bit like that. It's a weak link, a constriction, something like that. Okay, let's look at some of the basic physics of a Josephson junction. Here we have two superconducting regions. Again, they've got these Cooper pairs in them, and each superconductor can be characterized by a wave function. And between those wave functions, and the wave function has a particular phase. What is phase? We're not going to get too much into that right now. Just all you have to think about is that there's a phase difference between these two sides. And when there's a phase difference, there can be tunneling of the current of Cooper pairs from one side to the other. And the current phase relationship is that the current is equal to the critical current of the junction, which is a function of the area and how thin or how thick the barrier is, how easy it is to tunnel through the barrier, and things like that. So the critical current of the junction times the sine of the phase difference. Well, that means that the current starts out at zero with zero phase difference, rises up to a peak at pi over 2 phase difference, then drops to zero, goes negative, and comes back. It's a sinusoid. Okay, so if we um, have a little bit of a bias, if we say have a little current through here, and that means there's a phase difference. And then if we give it a little kick, a little bit more current for some reason, we can kick it over the top. It goes through a 2 pi phase shift. And that's a switching event. Okay. And voltage phase relationship for this tells us how fast the phase changes with respect to time. And it has this relationship that the voltage is equal to phase, the flux quantum divided by 2 pi d phi dt. And that turns out to be, if you rearrange it, 483 terahertz per volt. That's a lot. You get a lot of very high frequency out of these when they switch. Okay, an analogy for this, how this behaves, is that it has the same mathematical equations as a pendulum with damping. And you're applying a torque. It obeys similar dynamic equations. And so if we run a little picture of this, and the pendulum is matching the blue dot, the location of the blue dot on the current phase relationship. And you'll notice that when the pendulum is at, I guess that would be the 9 o'clock position, then that's like it's at the 0 point. Okay. Now these Josephson junctions in electrical circuits, we have a symbol for a Josephson junction. This is a bare Josephson junction, and you can get the symbol, you can find the symbol online. And but we have a circuit model where this Josephson junction acts like a phase-dependent current source. There's a capacitance and an internal resistance. And the internal resistance is variable because the current phase relationship looks like this. And the resistance is actually high and then it drops at some characteristic voltage. But it's a hysteretic. This is just for a bare, underdamped Josephson junction. It's hysteretic where we can apply a current and there's no voltage drop, and then when it goes over the critical current, it jumps and it has a resistance and a voltage. And then you go up, but then when you're coming back down, you come down here, and unless you go all the way to zero current, it can get stuck. Um, so these a bare junction has some problems in use in circuits. And so people found that if they added a shunt resistor around these things, and these shunt resistors will have a parasitic inductance as well, but you add a shunt resistor and you change the damping, um, you actually you're decreasing the resistance of the device in parallel with the device, and the quality of circuit, the quality factor goes down, and you can actually provide critical amount of damping. So what we want is this beta C value to be about 1, and we get damping, and this is what it looks like with beta C about 1, critically damped. We apply current to this, there's no voltage, goes up, and then when it switches, it'll switch, it'll go over, create a voltage, but then when it comes back, it there's no or little hysteresis, and it goes back to 0 voltage. So that's a device that we want to use for a switch. And when it switches switches quickly. You can see, depending on the how the junction is made and the characteristics of it, but on the order of a couple of picoseconds and about a millivolt is the switching. And it creates a little pulse. And if we integrate over the pulse, then it turns out that if we integrate the voltage as a function of time, we find that that is equal to the flux quantum. So we get one flux quantum out when it switches. And that does not depend on some of the details like the critical current or the area, or the shunt resistance. You get a flux quantum out. Okay. Now an analogy for this critically damped Josephson junction is it's a little bit like a baby drinking milk. You feed the baby and it's just fine. If the current, if the flow of milk into the baby is less than the limit, the critical current, the baby is happy. Everything's fine. And that goes for, and in this case, you can feed it through the junction either way. But if you exceed the critical current, if you have too much flow into the baby, then it spits up. And an interesting thing is it spits up one flux quantum each time. And that'll help you as a circuit designer to understand that you're putting current in one direction, when the junction spits up, the current actually comes back. Um, and maybe that's a little bit hard to see from the usual equations, but that'll give you a sense for what's happening. So we can make circuits with these devices. And in superconductor electronics, these single flux quantum circuits, um, inductance and critical current are linked. And those are the important quantities. Whereas for CMOS or conventional semiconductor electronics, it's it's charge and capacitance that's important. We have to look at inductance and currents. So for single flux quantum, you have a certain amount of flux, and that's like current times inductance. So we need the current times inductance in our circuit to be on the order of a flux quantum. Sometimes we want it to be a little less, sometimes we want it to be a little bit more. So the switching energy is determined by the critical current times phi naught. So the importance of the switching energy is that we need to be well above the noise limit, KB times T. So we want to be above the noise floor, and that's going to tell us what kind of critical current we need. Um, at 4 kelvins, we typically need on the order of more than 10 microamperes. So a good one, 25, 50, 100, 150. We need more, significantly more current than that. Now, if we decrease the critical current, it becomes more energy efficient, because for the single flux quantum, this quantity has to be conserved. If we decrease the current, we need more inductance. And we can apply that by wiring. Wiring has a combination of magnetic inductance and kinetic inductance, or we can use junction-like devices. Josephson junctions also have inductance. But we will need, if we need go with lower current, we needed more inductance. Okay, now there are a lot of challenges for superconductor electronics. Some of them are that fan out is, if you want to, you get one flux quantum out of your circuit typically, and if you want two flux quanta and you want to split them into, supply two different circuits, you have to provide a splitter. You can't just divide the wire and get, multiple. You gotta, you're operating in a very low energy region, and you have to provide splitters to have fan out. There's low gain, and let's see, low isolation across JJs, because there is a super current across them. Um, and there are alternative devices being explored. There's some examples down here, but we're going to look at circuits that are made with Josephson junctions. So, how does this work? Here's an example of a single flux quantum gate called a set reset flip-flop. So we start with this, and the way you can think about this is the blue is superconductor wire. So these are superconductors. And the yellow is a Josephson junction that's critically damped. So it's not showing explicitly a shunt resistor. It could be an internally shunted junction. Just in this circuit, these yellow things are critically damped Josephson junctions. Okay, and this can be like in an integrated circuit, this might be one layer of wiring, and then you've got vias. The junctions are in the vias that are going to another layer of superconductor. But they form little loops between the junctions. Okay, so the first thing we do is we apply a bias current. And that might have been a little quick, but you'll see that we applied a current, it went down, and there's no resistors in this circuit, but the inductance, the current splits through each of these branches based on the inductance, the relative inductance of the branches. In this case, the inductance is the same. We put it down the middle, and we get the same current through these two junctions, J0 and J1. Okay, so then we apply an input to the circuit, and that's going to be a single flux quantum will be the driver that provides a current into this input loop. There's some loop here. And that going, because the inductance, there's an inductance in that input loop, and there's going to be one flux quantum current times inductance. There's going to be some current that gets induced in that loop. Now, in this case, we've got the current coming in, and the original bias current was small enough that it did not cause the junction to switch. But now we've got two different currents that are adding up through this J0, and they're large enough that we design it so it's large enough so that the junction critical current is exceeded and it switches. So we get a pulse out of it, a voltage pulse, and it's like the baby spitting up, and it spits up and it causes one flux quantum of action back, and that shuts down completely this current that was in the input loop, and it creates another current in this other loop. And so after that happens, this is what it looks like. We now have a current circulating in the air in addition to the bias current, and it's as though the flux quantum went through the junction and is in here. So now we have two currents here. This junction now has two currents in opposite directions, and we design it so that junction is now happy and it just sits there. But this junction, J1, now has two currents that add together. It exceeds the critical current. That junction switches, it kicks back and shuts down the current in the bias, in the transfer block loop, the smaller loop, and it develops a current in the larger loop in this storage block. So this is a storage loop, and the inductance here is large enough that the current is small. Now this junction, the two currents, the smaller currents are in opposite directions. This junction is happy, and this junction only has a small current going through it. It's happy. The current circulates basically forever. So it's a storage loop. And things just sit like this until we decide to, there's a reset or a clock branch that we can put a current in. And we do that with a flux quantum that drives a current down through these junctions, J2 and J3. In this case, J3 exceeds the critical current. J2 does not. And so J3 switches. And we get a pulse out. And the kickback shuts down the current in the clock line, the reset line, and the current in the storage loop, and we get an output. Okay, so that's how that set reset gate works in the case where you have an input. Now, there's a second possibility. The other possibility is that there's no single flux quantum in the storage loop at the end of the clock period. In that case, When the clock pulse comes down, current goes down, and we have these junctions sized so that in this case, J3 is fine, but J2 is exceeded and it switches and shuts down that input current. And we get no output in the output portion of the circuit. Okay, so single flux quantum logic families. I gave an example. I didn't show how the bias currents were supplied. There are different approaches to doing this. One of them is to use resistors to send the currents where you want them. This is called rapid single flux quantum logic. That was developed in the 1980s and early 90s. And so it can operate very fast. However, the power dissipation in these resistors is over 90% of the power typically of the circuit. They can operate very fast, but they also dissipate power, and the current supply adds up, and it limits to the circuit size to tens to maybe hundreds of thousands of Josephson junctions in the circuit. There are more energy efficient approaches, ERSFQ, came out of Hypris, and it uses Josephson junction and an inductor to provide currents. There's a reciprocal quantum logic that uses an AC drive. There's also something called AQFP that's not exactly, it's not an SFQ logic family, although it's related. It is a superconductor electronic logic. There are many different approaches, and right now people are still working on which one of these approaches is going to be the one has the winning combination. Okay, so in conclusion, I have some references and resources. Some of these are more of these are presentations or publications that I've authored, but there are many other references and resources. Hope you enjoyed it. Thank you.